morning. Good to see
Good morning,
everyone.
Angela.
Hi, Ana Lucia. Hi, Ashish. It's really great you made it, and thank you for doing this. Just before that.
It's pleasure for me. It's mission driven, and I get paid for this
Oh, good.
out of my regular salary.
Yes, yeah.
Now, this is mission for me, to be able to get a chance to work with computer scientists, to be able to work with biomedical engineers, management school, is why I'm here, why I came to UC Davis. So
Excellent, excellent. Good. So we should build on this.
absolutely.
I don't know if Kim Barrett, our new Vice Dean for Research, will be able to join us. I think she is registered. I don't know if you met Ashish with Kim.
I haven't got a chance to meeting, but I'm planning something in January to have a detailed meeting with her.
Oh, good, good. Excellent.
I have a slides which will not take more than 5 minutes.
Perfect, thank
If
you.
I do, you can bump me, and I have my last slide where I'll be introducing Chandni Chow. Is that how I should say your name? Chandni?
Yep. Yeah, Chandni Chow.
Okay, wonderful.
Thank you.
I practiced a lot of times, so I'm glad.
If you want, actually, I can share my slide while you're introducing, then you don't have to make an extra slide.
No, it's just your picture and your title.
Okay.
You're all set. I can never do justice to your slides. Great. And Vladimir is coming as well. The key messaging I want to give is how we are trying to get campus and health system together, and and this initiative is right in the middle of it. We want to liberate our health data, leverage all the intelligence and all the expertise is there in the campus, but also build partnership with clinicians who may sometimes have that knowledge. Causeway should be Causeway should mean collaboration and not a separation.
Yeah, theoretically.
No, the only people who can bridge the gap is us.
Yes, that's true. That's true. So it's really great. We started this just after the pandemic hit with Ana Lucia, and it kind of evolved. So Ashish, it would be really great if you could stay sort of part of it, and maybe you could also influence some of the sessions that we are planning. So if that's okay with you, we will involve you.
I have a conflict with the CIO meetings UC wide that I have to break away. But what I'll do is, as soon as that is done, I'll come back, and I also watch the recording.
Perfect.
So it's just, this is mission driven for me.
Perfect. Good morning, Prasant. Morning, Paul.
Good morning. Good morning.
Angela, how are you?
Good, good.
Hi, Vladimir. Hi, Prasant.
Hi.
Hello. Morning.
Right.
Hello.
We are almost ready. I'm waiting for just one more. Oh, here she is. We have all of our speakers. We have all of our speakers here. We have a pretty tight agenda, so I'm just going to ask all of our speakers to be observant of the time that was allotted to your presentation. And I just want to thank everyone because it's the last session of the year, and we'll be back in January with more content. And I'm hoping to hear from you with your suggestions. Your positive, constructive criticism is always welcome. And with that, I'm just going to hand it over to Prasant. I'm going to go into the background and wish you all really great holidays, and hope you are able to take a little bit of a break over this break.
Okay, thanks, Ana Lucia. Looking at the speakers list, I feel this is my home ground. But before I welcome everyone, I would like to sincerely thank Ana Lucia for helping and coordinating this whole series. So Thanks a lot, Alicia. So welcome everyone to this is the last team research forum for 2021. This year we hosted 16 sessions of the forum ranging from topics related to the COVID variants and vaccine development, healthy aging, DEI, indoor air quality, and I'm sure I'm missing a few others. We had several high profile speakers similar to the ones we will have today. We had Kathleen Carrico, who was the original founder or inventor of the messenger RNA approach that we are really indebted to now. So we had also David Kessler in as one of our speakers. We'll continue to work hard to bring more and more speakers at that level during the next year. So we are working on planning the sessions for winter and spring. So if you are interested in hosting a session, or if you have connections to bring some high profile speaker, please get in touch with Ana Lucia. And again, if you have new ideas also on how to promote these team research activities, out to Ana Lucia. So today we are revisiting the topic of AI, machine learning, and health. We last had a session on this, which many of you attended on February 5th. And we have invited researchers to come back and talk to us about their progress and challenges working in this area. So co-hosting today's session with me is Dr. Ashish Atreza, so from the School of Medicine. So my role is to introduce Ashish and let him run this Q&A and everything so that I can sit back and relax. Thanks, Ashish. So Dr. Atreza is the Chief Information and Digital Health Officer at the School of Medicine and is overseeing the expansion of digital health at UC Davis Health. Dr. Atreza is a gastroenterologist and previously served as the CIO for the Department of Medicine at Mount Sinai Hospital. At Mount Sinai, Ashish established one of the first innovation hubs within an academic medical center to build and test disruptive digital health technologies, those that have had a huge impact on the industry. Okay, let me pause there and hand it over to you, Ashish.
Thank you so much, Prashant. It's tough to follow after you, but I was just saying this is so mission driven for me. One of the reasons I came, here was to be able to partner with the campus to really leverage all the knowledge, all the expertise that's across so many fields in the campus, and really align them with the healthcare mission that we have, delivering tomorrow's healthcare. So, and all the speakers here, the goal is we learn together and we build things together. I just want to take a few minutes just talking about where we are going as a health system, our vision. So with Dr. Lubarsky, we're on a track to become a fully integrated academic health system, but really delivering tomorrow's healthcare today, right? We want to be most future friendly, most future proof, but bring all the latest technology in the right manner. So our patients, our clinicians, our researchers, our educators, and our partners can benefit from it. And that also requires a new way of doing things. So we have reorganized our IT into innovation technology. So our 600 people IT group, every one of them, we are calling themselves and training them to be an innovator. And we've created a centers for excellence. And those are not just centers for excellence around IT applications in Epic or infrastructure, but also around data as well as Colab, right? So we want to really enable us to be a digital and data first organization. And each one of those centers have a mandate, have a project charter. So basically we are creating organization units which can formally support you, not just in an ad hoc manner, but actually their charter and their mission is to support collaboration around data and to enable us being digital and data first. And from the data side, I'm sharing some of the work that's already happening. The key thing is how to liberalize our data to make it available to across the causeway and with our key partners. So we already have all the UC-wide data beyond UC Davis being mapped in OMOP standards and available in both identified manner under the right jurisdiction and de-identified manner. And that can be available for research. So these are the different data warehouses that we already have on a cloud-based platform. We're using Azure for that. And this is the breadth of the data fields that is currently available. So we're still putting more self-service tools on top of it. But my request is for you to actually start leveraging the data. If the data is not leveraged, there's no value of the data. We want to just walk with you over the next Q1 and Q2 in 2022 to get the right kind of governance, the right kind of stewardship, and the right kind of framework. So you are able to get the right data at the right time to deliver the right models that you have. But that's where we are embarking on a journey to liberalize this data for across our causeway. We also started working in Databricks environment, as many of you know, to not only have clinical data, but combine the clinical data with maybe environmental data, which many of you may have, with genomics data, radiology and pharmacy data. So to really kind of make it much more rich, multidimensional data for all of us to get value from that. And working closely with the campus to actually have computing cloud, across different cloud environments using the lake house concept. But just having data is one part of the story. We also want to build collaborations and formal engagement models. So we have set up an organizational unit called Digital Collab to not only partner within our organization with campus and health system, but actually partner with external partners as well, with the industry, so we can do very meaningful stuff and scale our efforts in a way that was never possible before. So the goal of Digital Collab is to really partner with industry for co-ideation, co-development, so we can do co-transformation. And one of the central part of that is we can validate AI models together across different patient units, or generalize it before we actually leave it to production. And the goal is to make Aggie Square, which is a combined effort by the campus, the health system, and the city of Sacramento, as a home for healthcare digital and data validation and transformation. So that's a lot of square foot, but we really want to work to create a digital sandbox with synthetic data as well as the data we showed to really allow us to partner meaningfully with industry as well. And we had also had a very big announcement to make. Just last month in AWS reInvent, which many of you participated, we actually announced we are the first health system globally, which AWS and Amazon has reached out for a Cloud Innovation Center partnership. So, and this created a lot of buzz in the market. So we're certainly being deemed as a leader in digital medicine because of our relationship with Amazon and AWS. And AWS is committed to not only commit FTEs to us, but also give unlimited AWS cloud credits as far as it's for the cloud innovation and open innovation model. And what we hope is this will allow us to build a lot of capabilities inside on how we can harness the cloud, actually scale all of your efforts. So I just want to end on this note that we're on a mission to liberate data and build collaboration across the causeway, across UC, and actually eventually globally. And I'm sharing the emails of Kent Anderson, who leads our Data Center for Excellence as a single point of contact for data collaboration, and Dr. Kei Nakagawa, who is leading Digital Collab for industry partnership. So I look forward to working more and more with each one of you and kind of supporting our common vision around that. It's my pleasure to introduce our first speaker, Dr. Chandni Chow, who is a child family professor in engineering and Department of Electrical and Computer Engineering at UC Davis. Chandni, please take it away. Thank you very much.
Thank you. All right, let's see. Can you see my slide okay?
Yes.
All right, cool. Thank you. Good morning, everyone. So today I just want to kind of give a brief overview of the different ML AI in health projects in my group. Just to give you a little bit of background, my background is actually computer networks. In the past, I've studied a lot of complex network systems and applications. And in the last 5 years, I have started several collaborative projects with our colleagues in the School of Medicine. And I'm still learning a lot about the various other activities there as well. So in my group, we are interested in innovations across the data pipeline. And I will explain a little bit what I mean by that. So the medical data inherently, is heterogeneous and is noisy and is volatile as well, depending on the patient conditions. So the first step, right, is to acquire high quality data that we can actually use to train the machine learning models. So oftentimes we found ourselves actually spending a lot of time at this stage of the data pipeline. And we had to come up with innovative algorithms to automatically detect artifacts, for example, and also detecting features and extract features that are deemed important from the clinicians that I work with. And then depending on the source of data, there are various ways of applying image and signal processing techniques there as well. And then once we have those data, then we can apply statistical machine learning, deep learning, anomaly detection, depending on the learning task at hand. But one of the things that our group is interested in is to build a robust machine learning model that can be generalized to different heterogeneous type of settings of the same type of data, as well as a label efficient learning, because we realize that the annotation efforts, right, from the clinicians to label the data set for us to train the supervised machine learning model is very label intensive. And so we oftentimes are dealing with a small label data set, right, rather than a large data set like the image data set that is used to train ResNet. And then lastly, we're also interested in data-driven decision control and support. And this piece is kind of related to the translational research piece. It's very important for us to actually be able to interpret the models that we come up with and also quantify the uncertainty of our prediction and the impact of bias fairness issue, depending on whether or not there is an unbalanced data set and unbalanced data representation from different subpopulations. And in order to deploy this, we are also worried about security and privacy issues that we try to address in the lab. So today I want to basically talk about kind of 3 different categories of projects that are ongoing in my lab. The first category deals mostly with time series data. These are biological signals that we collect from the patients. Sometimes we kind of augment it with the EHR data with a goal of developing an AI-assisted clinical decision support system for early diagnosis and prognosis. And then the second project deals with medical imaging. And this is in collaboration with Dr. Dagger. I saw her in the participant list at the Alzheimer's Disease Center on campus to phenotype human brains. And then the last category, we deal with video data. We use video data to look at behavioral detection for autism spectrum disorder screening. So I'll first go over the first type of project where we are really interested in AI-driven critical care. So the first project was in collaboration with Dr. Jason Adams, and we are looking at the mechanical ventilator waveform data and try to use that as an objective data that we can monitor continuously to perform early detection of ARDS, which is acute respiratory distress syndrome. It affects about 25% of mechanically ventilated patients. And for those who have moderate or severe ARDS, actually the mortality rate is pretty high. And this is actually of relevance to today's pandemic, right? Given that a lot of COVID patients ended up being mechanically ventilated. So we actually look at the entire pipeline of how to get the data out from the mechanical ventilator to the 3 stages that I talk about, data acquisition, and then we apply machine learning techniques, and then to trying to come up with an interpretable model. And the same pipeline, actually, we also expanded and looked at multimodal data for the second project in collaboration with Dr. Austin Johnson and Jason as well, to look at waveforms such as blood pressure in addition to ventilator, And then we are trying to predict whether or not a patient is responsive to fluid administration, the fluid boluses that are given. And then the last project was in collaboration with Dr. Sivkas in the pediatrics department. And we're trying to look at the oxygenation, the pulse ox waveform from the finger and the toe of the babies. And these are for newborns to detect critical congenital heart disease. So now let me kind of step back and take the first project as an example to look at, what are the types of things that we'll look at this few years. So the concept of, from bedside to cloud, this basically involves us actually deploying Internet of Things or edge devices like the Raspberry Pi in order to stream out these waveforms that we are interested in collecting to a server, storage and compute server that is behind UCDH firewall. And that's where we kind of can develop algorithms to analyze this data. And then to close the loop, we also develop an iOS app so that, Jason, for example, can actually view this waveform and the analysis from our algorithm in order to give us feedback whether or not, for example, the anomalous breath that we detected or the ARDS condition is truly ARDS condition or an anomaly. So I mentioned that we are interested in interpretable model. So for this particular project, at first we were working very closely with Jason. We tried to understand what are the expert features he will look at in order to define or try to detect whether or not the patient has ARDS. And based on the expert features, right, we can train classical supervised machine learning models like random forest in order to detect ARDS. And we got pretty good performance, right, AUC of 0.88. And then we asked ourselves, can we do better if we just use the raw waveform? Are we missing anything? Because these are based on expert-defined features that we have to manually do the feature extraction, right? We extract these features from the waveform first before we train it. Now, by feeding the raw waveforms to the 1D CNN model, we actually get even better performance, AUC of 0.95. But the deep learning model, even though the nice thing is that you can feed it raw waveform without the feature engineering step, but it seems like a black box. So we're trying to understand what is the 1D CNN model learning that gives us this advantage. So we actually perform a bunch of frequency ablation studies. So we basically filter out, have a different cutoff frequency for the raw signals. So on the right-hand side, these are basically the flow waveforms from the mechanical ventilator machine, and we apply different filters with a different cutoff frequency and reduce that from 20 to 5 hertz and feed that into our 1D CNN model. And then what we found out is that the performance of the 1D CNN model started to decrease as we approach about 5 hertz. And then around 1 hertz, it actually approaches the performance of random forest. So what it's telling us is that the DNN model is learning from both the low frequency and high frequency range. Now, if you look at the figure on the right, when we filter out high frequency signals, essentially what we are getting is the envelope of the waveform. And typically the expert defined features are derived from the envelope, right? The peak, the valley, the volume under the curve, like the inspiration, expiration volume, or the inspiration, expiration time. But what this 1D CNN model is learning beyond that, because it's also learning from the high frequency component, which is usually pretty hard to manually featurize. So one of the things we are also interested in the AI-assisted critical care is also trying to deploy this and look at deployment at the edge, right? So we're interested in lightweight inference on portable devices so that they can be deployed on the field or in a remote clinic. So we did implement our model on the latest NVIDIA Jetson Nano platform. Is an embedded system with GPU and CPU, and we get really good inference time. But before we celebrate, we also actually are very cautious about security and privacy issues, especially we are sensitive to the privacy concern, right? So whenever we have medical data, it's sensitive, right? There's privacy concerns, as well as the inference result, right? The patient might not want other people to figure out whether or not they do or do not have the disease. And then the AI ML model parameters might be sensitive as well. So in our recent work, we actually unfortunately found possible vulnerabilities, right? So it's possible to fingerprint exactly what type of ML AI model we are running using simple utility tools to track memory and GPU usage. And we have a recent paper in 2022 also showed that if the attacker can launch side channel attack on the victim DNN models, you can observe the execution computation graph and then deduce the inference result. So in our ongoing work, we are trying to figure out defense mechanism against this type of attack. Okay, so now I want to switch gear to talk a little bit about medical imaging, right? So this is in collaboration with Dr. Dagger at the Alzheimer's Disease Center and Pathology Department. So the pathologists are interested in looking at the density distributions of various plaques, right? Like, for example, the amyloid beta or the CAA in the gray matter and white matter region of the brain. And the current approach involves manual annotation of these digitized tissue images. And then they look at the plaque and then they count, right? And compare the density distribution. So at the beginning, when we had that conversation, right, with Dr. Dagger, our goal is to automate this entire pipeline, right? Both the gray matter, white matter segmentation, as well as the detection of the plaque. Now, this is possible, but one of the issues, as I mentioned before, is we are dealing with very limited annotation sets. So can we build a robust and label efficient model? And second, for different annotator, you also may have inter-rater variability. So towards this end, we combine semi-supervised learning and active learning so that we can make use of the large amount of unlabeled data set. And then active learning can help us select the most optimal data for labeling. And then lastly, I know I'm running out of time, so I just want to briefly mention that the collaboration with my institute, we are using video data to try to do an early detection of behavior that is indicative of ASD. So the type of hand-coded data that we have are basically videos taken in the clinical environment. And it's an annotator set because it involves human annotators to annotate the 4 behaviors of events that are of interest: look, face, look, object, smile, and vocalization. So where we come in is that, again, the annotation effort takes a long time. And so we are applying computer vision techniques to extract facial landmarks from this video, and then trying to detect the behavior of event based on those facial landmarks. And it serves two purposes. We can find the most informative unlabeled video segments to reduce the efforts, right? Kind of find the needles in the haystack. And secondly, eventually we will want to replace that so that we can do automatically coded this video for the behavior and then train a classifier to detect ASD. So, we have pretty good results. And then also for this project, we know that video data is very sensitive. So we also look at applying differential privacy and GAN to generate syntactic data that can be shared outside of our institution. So I think that's all that I have today. Thank you.
Thank you, Chandni, for your presentation. I'm going to invite the audience to place your questions in the chat box for Chandni. I think she needs to depart the session early today, and we are planning to have a QA at the end of the session. Our next speaker is Professor Thomas Stromer. He is the director of the Center for Data Science and Artificial Intelligence, CDAR, and he's also a professor in the Department of Mathematics at UC Davis. And today he's going to talk to us about democratizing health research for critical care.
Thank you very much, Anosia. Yes, you can go to the next slide, please. Before I want to start talking about the particular project, let me say a few words about the Center for Data Science and Artificial Intelligence Research, or CIDA for short. I talked about it already at the previous team research forum, so I want to keep it brief. Our society faces a lot of great challenges, like fighting climate change, trying to find sustainable food supplies, and trying to get affordable healthcare for everyone, for example. And the very ambitious mission of CIDA is to play a key role in bringing AI to these grand challenges of our society to make some real breakthrough solutions. The initial areas of focus are listed here on this slide, and you see these are all areas where Davis has a real strength. And please, next slide. And to say a few things about the particular role of CIDA at Davis, let me just point out a few things. CIDA is the hub for fundamental and applied research related to data science, AI, machine learning at UC Davis. And as such, one of our roles is to be engaged in the education and training of students and postdocs related to data science and AI. And as an example, we were heavily involved in the creation of the recent data science major that will start next year. And another important role is building synergies across faculty, across the campus who are working in data science, first to advance research, and second, of course, also to attract very large-scale grants. The CIDA is really transdisciplinary. We have over 40 faculty from 18 different departments and 7 different colleges. And so you see really truly reflected the interdisciplinary nature that you have built in data science and the AI. And one particular important topic is, of course, fostering and building the connections between UCD and UCD health related to AI. Next slide, please. Now, in this topic that I'm presenting today, I have 3 collaborators who are actually from UC Davis Health. I have other collaborators from other universities as well, but these are the collaborators from UC Davis Health, and they play a key role in this project. Nick Anderson, on the right, is the one who introduced me to this topic, the important topic of privacy and synthetic data that we already heard about in Chandni's talk, and actually already mentioned indirectly in Ashish's introduction when he talked about sharing data. Jason Adams and Rachel Calcutt are the experts who keep me grounded and point me in the right direction when we develop these tools and when we try to make them really practically useful. Next slide, please. And as you saw from the title, the goal is to democratize healthcare research. And Ashish mentioned already the importance of sharing data, otherwise data are not really useful. And this is in a way what this project is about. We also heard from Chandni's talk the sensitivity issues that we face when we deal with research in healthcare with patient data. And so privacy and healthcare data always go together and always form a very contentious pair. The issue is really paramount in the intensive care unit because it is one of the most data-driven environments in the hospital. And here we really, like in many other areas as well, but here it's really pronounced that we need good AI, good machine learning tools to help us in the decision-making. That, of course, means we need access to data, and this is a roadblock. We encounter a lack of availability of data. Ideally, we do not just want to share them within Davis, but across the UC campuses and across all hospitals in the US. And these privacy laws that exist are, of course, exist for a very good reason. Google, Facebook, and all the other companies that work, was business model is built on violating our privacy, show us time and again that we cannot trust companies with our data. We have to be really careful. And so these rules are here for a reason. Next slide, please. But the question is now, what are we doing with this? In this particular project for the ICU, we use one particular syndrome as a guiding model for us so that the tools that we develop are actually really useful in practice. And it is the syndrome that Chandni already mentioned before, the acute respiratory distress syndrome. So I'm not really talking more about it because Chandni already mentioned it, except that it is really a common and deadly disease. And if you're not diagnosed properly and treated properly, well, you can do real harm. And we have seen nicely in Chandni's work the importance and the power of AI, that how it can improve diagnosis. And what we also have seen is, however, if you really want to improve further, you need access to more data. And then again, we hit the roadblock. How do we get access to more data without violating users' privacy, people's privacy? Next slide, please. And this leads me to the topic of privacy-preserving machine learning, a flourishing area that's getting more and more attention. There are several ways to address this, and I listed 5 of them here: homomorphic encryption, federated learning and on-device learning, anonymization, differential privacy, and synthetic data. In this talk, I want to focus on synthetic data. First, homomorphic encryption is not really usable yet for these large-scale machine learning models. I know there's some recent results in that direction to improve this, but it's still far away from really being useful to the extent that we want. Federated learning on device learning is limited to certain setups. Anonymization is often brought up, but it's really very, very limited. From the outside, you might think this is a good tool, but it's easy to crack. So that leaves us essentially with differential privacy and synthetic data. Next slide, please. So what are synthetic data? Well, synthetic data are data that are generated from the original data, but in a way that they maintain key properties of the original data, and without exposing private information of, sensitive information about the real data. So you see immediately that's an intrinsic conflict in the definition of synthetic data. On the one hand, they should be similar to the original data. On the other hand, they should be different. And let's look at 2 very extreme cases. I could just use as synthetic data the original data. Then I have perfect utility, but of course zero privacy. On the other hand, I could just release random data, then I have perfect privacy, but zero utility. So you see there's an intrinsic conflict here, and this is expressed mathematically often, that many of these problems you encounter when you try to generate synthetic data in a rigorous way, many of these problems are actually NP hard. For the non-experts, it means we encounter computational problems that are essentially infeasible. They're not doable. So we need to do something really smart to make progress here. And the holy grail here is, as proposed by several experts in privacy, could we combine differential privacy with synthetic data? I will not explain what differential privacy is here in this talk, just that it is a one standard of trying to preserve privacy to some extent. Next slide, please. Let me instead describe the basic concept of anonymization differential privacy with help of this little image here. On the left side, you see images of faces. And on the right upper side, you see what would happen if you do classical anonymization. This, of course, this is meant as a schematic illustration. It's not literally what is done, but in principle, this is what would happen. It would block out certain sensitive information. Of course, you lose important information that way, and if you link it properly, you can still see which people these are. So it often does not provide the privacy protection that you think it does. And that doesn't matter if you use strong anonymization or not. It's always so far breakable. Differential privacy instead adds noise to the data. This is illustrated with the lower left, right picture here, which means if you add enough noise, you can hide the sensible information, but obviously you lose important information at some point. Next slide, please. Synthetic data instead tries to take a different approach. It tries, on the left side, you see the original data set. On the right side, you see a synthetic data set. None of these faces on the right side are real. They're all completely synthetic. They do not exist. Yet they look like real faces. So what we hope with this is that the faces on the right side, well, they look like real faces. It doesn't mean they represent the underlying structure of the original data set, right? Do we have the same representation of different groups? So we have to, just by constructing such faces, that doesn't mean much. What we have to ensure that is that the synthetic data set really captures these nuances of the original data set. This is not easy to achieve, and this is one of the key questions. And at the same time, you need to ensure that it doesn't reveal information. We have heard that in Chandni's talk, that this is a very tricky issue, and you might, have privacy leakage when you do not even think you could. So synthetic data tries to achieve this goal of preserving the information that you want and hiding the information that you should. Next slide, please. But it gets more challenging in the ICU setting because the data are not just one type of data. They are heterogeneous, dynamic, multimodal. So you have waveforms, you have images, you have patient records, you have maybe spoken data and so on. And you need to combine all this, next slide please, to create a framework that can construct synthetic data. And this is the goal of this project that has been recommended for funding by the NIH. So the goal here is to develop a framework for the creation of synthetic data that are accurate and privacy preserving, and do it in a principled way so that you can really be sure, so it comes with theoretical guarantees. So not just some empirical tests that would not really satisfy a lawyer, but provable guarantees that would hold up. And we want to use, or we are using ARDS as our guiding syndrome that keeps us grounded, making sure that the results that we produce are actually tested in practice. And that comes to brings us to the last point on this slide. We want to create, or we are creating, a closed feedback loop by working closely with UCDH, with Rachel and Jason. We are in a great situation where we get data that are real data. We can use them, we can construct algorithm, feed them back, test them on the real data, test them in a real situation, and then improve them. This feedback loop, I think, is what will make this project a real success, and hopefully develop tools that are usable beyond this particular project. Next slide, please. That's the last slide. The previous speaker, Jeannie, is co-director of CEDA. The next speaker, Shin, is co-director of CEDA. Nick Anderson, who is part of this project, is co-director of CEDA. I'm also representing CEDA. So instead of saying more, please check out our website and, of course, the next talk by Shin. Thank you very much.
Thank you, Thomas. Our next speaker is Professor Xin Liu. She is a professor in the Department of Computer Science at UC Davis, and she is co-director at the Center for Data Science and Artificial Intelligence.
Sorry. In trouble with this. Okay. I don't think you're seeing my screen appropriately. Okay. Does my screen show up appropriately?
Yep.
Okay, thanks. Thank you, Ana Lucia. So today I'm going to talk about a specific topic of using AI for healthcare applications. Specifically, we focus on sensing data. So let me introduce myself a little bit. I'm a computer science professor. I've been here for 18 years, and in the past 7-8 years, we have been mostly working on machine learning algorithm development and machine learning applications. So let me go to the next slide. So there are a large variety of different types of sensors available, both off-the-shelf sensors on mobile or wearable devices, and more specialized medical sensors that are primarily used in medical facilities and research labs. For off-the-shelf devices, the popular ones include accelerometers, gyroscope that we can find in every mobile or wearable devices, regular cameras or infrared cameras, heart rate monitors on, say, Apple Watch, or continuous glucose monitoring devices for diabetes patients. In medical facilities, we have different types of electrodes to collect brainwave signals, ultrasound and other imaging devices, force plate or specialized treadmills for motor studies. Using these, the widespread of these sensing technologies, especially with the widespread of mobile and wearable devices, have enabled much larger scale and finer grained collection of physical biological data of both patients as well as the general population. From a machine learning perspective, in our work, we mostly see this data, such type of data, as time series data. And using machine learning, we could classify patients versus control. We could identify hidden patterns that are not obvious to human eyes. We could provide more objective and quantitative analysis of disease in terms of, for example, severity or progression. Furthermore, such automation as well as systems could also empower remote medical care and enable much wider scale of preventative care and intervention. So in this talk, I want to illustrate the potential of such AI-based sensing technology using a few examples from our ongoing collaborations. The first project I'm going to talk about is a joint work with Dr. Eric Harrison from the Department of Physical Medicine and Rehabilitation. We have studied DMD patient identification. DMD is a generic disorder characterized by progressive muscle degeneration and weakness due to the alternation of a specific protein. And this DMD symptom onset is in early childhood, usually between age 2 and 3. It mostly affects boys and sometimes girls. Oh, this is a picture of Dr. Eric Harrison, our collaborator here. He has been working on DMD for many years. In this project, we have developed a system consists of an iPhone app that collects movement data and also using phone's built-in accelerometer. So this is what it looks like. And this is how it's attached to a subject that we're running the test on. And the system also includes a cloud-based tool to aggregate, visualize, and store data. You can probably see on the screen of Dr. Harrison in the picture. And also include a set of machine learning algorithms for gait analysis. I'll talk about the machine learning aspect a little bit later. So this picture roughly shows how I should say Dr. Harrison ran this experiment, ran this remote clinic during the pandemic. This is actually not a patient, I believe it's his son, but this you get an idea. And this is through Zoom. This is how the device is attached to the person. And this is what we see on our cloud servers. This is a picture, this slide shows what signals we collect. We basically collect X, Y, Z signals. And the first picture is in a 2-second time window where the bottom one is for the entire duration of the experiment. And we have two lines here, blue and red. One is control, one is DMD patient. In this work, we have evaluated 3 different flows of machine learning schemes for classification of DMD kids with typically developing kids. We use the classic machine learning with features generated by domain experts. We also use classic machine learning with raw accelerometer data. The third one is deep learning with raw accelerometer data. This is similar to the results Chandni showed earlier. We actually see deep learning algorithm using raw data generates overall the best results among patients. Among people in this case. By the way, the first 3 bars, the first 5 sites are kind of calibration tests, where the last 2 are the real diagnosis tests. So in summary, in this work, we have developed an operational system for community-based DMD screening and monitoring. Basically, a person who is concerned about this, the patient may be a few hundred miles from the closest specialty clinic. They can download this app. We can run this clinic remotely with a patient. And we actually have done this during the pandemic. It shows good performance on common clinical gait parameters. I didn't show this in the slides. We also show good classification accuracy at a fast walking speed. So we're continuing this work. First, we have already developed an Apple Watch version of the app. The goal of that is to be able to collect data 24/7 so that we see how patients and control behave in their daily activities instead of the controlled tests that we run for half an hour or so time. And also, we hope to use this tool to study progression and also the effectiveness of different intervention techniques. Also, what we are doing right now is to look at the interpretability of such time series data. As I mentioned earlier, the classification accuracy is actually the highest in deep learning models. look at this time series data. And the question is, well, which part of the signal contributes most to the diagnosis? And in this case, we could correlate either with clinical features that domain experts already know about, or we can even work with domain experts to see are there additional patterns or features that could contribute to the diagnosis. It's also worth mentioning the system and the approach are generally applicable to many motion-related sensing studies. So I'll mention two of them in my later discussion. One is for motor function study, one is for ADHD study. And I also believe this is very relevant for healthy aging as well. So the second project is a ICU patient early activity identification project. Again, with Jason Adams. He seems to be the most popular collaborator in today's presentation. So I'll go through this quickly. The idea is, well, for ICU patients, early mobility activities of them is a key indicator of their recovery and so on. And doctors want to have a good understanding of their early mobility and potentially prescribe appropriate actions. So Jason and his team has collected data for a number of ICU patients using two accelerometers, one on the chest and one on the side. In this work, we have mostly performed the data analysis. We look at the sensor, again, accelerometer data, and see if we can identify patient activities during this ICU stay. We have looked at the amount of data, the performance affected by the amount of data and activities, and also later label accuracy, because the label in this case is also of low granularity. Right now, we are also looking at multimodality data, basically because ICU patient movement is much harder to identify due to the nature of patient movement. They move much slower and they have much deformed format. So we are looking at if we can use video data to augment the identification. A key challenge here is, of course, we don't have annotation of these activities, or we have a very small amount of annotation. How do we address such challenges? So these are the two projects I'm going to talk. I've talked about a little bit more in detail. The next, in a few minutes, I'm going to give you a broader overview of some ongoing project. The goal here is to see the potential of such AI-based sensing in healthcare applications. So for these brief discussions, sorry. For these discussions, I will mostly focus on the data source as well as the objective of the study. So the first work we're working, the first one I want to talk about is working with Professor Caroline Patton. She has been working on developing prognostic indicators of motor recoveries after stroke. Working with her, we are developing machine learning algorithms to study such indicators. And there exists a significant amount of variations, not in the evident indications of stroke, but also the course of recovery. Furthermore, such motor analysis in motion labs is labor-intensive, time-consuming, and requires expensive equipment such as specialized treadmill or force plate. Our preliminary study research results have shown that we can use machine learning techniques effectively, similar to what we have been using for motor study, and compared to traditional methods that have been used in the field, we can use data much more efficiently. In addition, in this project, we are, in addition to the goal of classification, we are also interested in identifying key measurement component. So for example, the idea is, right now they use treadmill, force plate, cameras to analyze patient data. But if we want to use this more broadly, say in a community center somewhere, can we reduce the usage of these expensive equipments? And also a long-term goal is we also want to develop more objective severity metrics. So that's kind of the goal we are going after. The second project is identifying hemorrhage stroke, and this is a collaboration with Dr. Kevin Keenan. I believe he's in the audience. The data source we collected is, so this is a kind of interesting study, to me, a very unexpected scenario. So Dr. Keenan and his colleague have studied stroke patients. Some of them have massive brain bleeding. Such patients need to be sent to a specialty hospital so that they can be treated appropriately and fast. They have built a helmet in which the accelerometer can pick up different signals from patients with and without hemorrhage during the stroke. We are in the process of developing machine learning tools to do such classification. Yet another project is for ADHD patient classification. We are using ActiGraph, which is basically a type of accelerometer data from about 300 ADHD patients. This is joint work with Dr. Julia Switzer. And our first goal is to identify ADHD patients. Then we want to study the correlation between movement and concentration, and possibly the effectiveness of different interventions. So for example, if you see a fidget ball and people use it, is that really effective or not? And the long-term goal is also more objective diagnosis of ADHD. This is a project with Dr. Will Joyner. The data we get here is from ultrasound images of children with limb deformity. The goal is to identify patient movement patterns, so eventually we can use that to precisely control prosthetic devices. This is a really interesting stage in an early stage, a really interesting project in an early stage. The project involves multi-modality data from continuous glucose monitors, accelerometer, heart rate monitors, and in-clinic access notes. The goal is to develop safe and in-home exercise programs for cardiac rehabilitation for patients with diabetes.
I hate to interrupt, Shin, but we're eating into the next speaker's time.
Okay, sorry. I should sum up. So this is another study related to brain activity study. So let me summarize. So we see time series data generated by diverse sensors as a potential to use AI technology and for healthcare applications. We see a lot of potential applications, and hopefully we can have good collaborations between the campus and the healthcare systems. Thank you very much.
Thank you, Shin. So this brings us to the last speaker of our session, and we will have time for discussion and Q&A after this last session, so we invite you to stick around. Our last speaker is Professor Vladimir Filkov. He's a professor in computer science, but he's also the director of translational science at Data Lab at UC Davis. And today he's going to talk to us a little bit more about the efforts at Data Labs to work on health data and how you can engage with their group.
Yeah, thank you. Great to be here. I was just actually enjoying myself with Shin's talk. Sorry, Shin, you had to cut it short. Looking forward to seeing the full talk. So I'll try to go faster so we can have time for questions. So I'm a professor in computer science also, but my main role for this talk is the director of translational data science. So my portfolio at Data Lab is and mandate is really expanding Data Lab and meeting the need of the health data science projects out there. And I have been having a blast over the past year plus, talking to people and networking and trying to understand how Data Lab can really help and develop ourselves into a more professional, service as research unit, a research as service unit. Sorry. So just for completeness, Data Lab is the grown-up data science initiative. The Data Lab exists for the past 3 years, has been growing strongly and working across campus, and now, as of late, increasing its presence on the UC Davis Health Campus. Our mission is, of course, to do research, training, and delivery of services to accelerate discovery in data science and to help campus in that regard. We operate through 3 different modes and many little sub-modes, but we have research, training, and community building. We are supported by the Provost and the UC Davis Library, and we are, as I said, a pretty grown-up service. We have our executive leaderships, we have data scientists, and we have GSRs, we have postdocs, and I'm going to thank all of them at the end. So one part that's very interesting in Data Lab is that we also have, through the community engagement, we have our learning clusters, research and learning clusters, and one of them is the health data science research and learning cluster, which is growing strong. Our goal is to provide data science related know-how to researchers on campus and the medical center, and to provide data science support for UCDH's operational needs, and in general to enhance the competitiveness of our healthcare and research in health data science. So who is in our community? We have our collaborators, research PIs from UCDH, School of Medicine, School of Nursing. We have trainees from School of Medicine, mostly faculty. We have research students and staff. And our partners who are working with us in growing this are the leaders from UCDH IT. Thank you, Ashish and Jason Adams, for your support and partnership, the School of Public Health, CTSC, and others. And our modes as a research as a service have been inherited from the wonderful work people have done figuring out the data lab service modes. And we engage in office hours, which are short engagements, first come, first serve. We have consultations, one-on-one meetings, appointment-based. We have workshops, demos, talks for training and learning. And then we have the particular collaborations that I'm going to talk about now, which is limited duration collaborations. These are periodic 10 to 12 weeks of resources dedicated to help a particular PI or a group of PIs to build some infrastructure, to provide pilot results. And then we have longer research collaborations by participating in grants, MOUs with different units on campus, especially UCDH, IT, ad hoc projects that come from time to time. And these are longer, they take 6 months plus. And we also operate as a recharge-based core, and that's coming up in the pipeline. It is being developed. So I will talk about both the limited duration projects and give example of those, and then our longer term projects and give some examples of those. And then I'm going to tell you about the lessons we've learned from participating in tens of projects with people at UCDH, School of Nursing, Vet Med, and others. So what do we see in these limited durations projects? So these are typically PIs who come to us and then have a particular need in data science, and it can be from a very basic, gather data for us to let's analyze the data using GANs and other type of sophisticated deep learning methods. But they span the gamut, and as I said, they have different needs are involved. But we see all sorts of things from those that we already saw, like medical image analysis, data collection, cleaning, patient record analysis, patient monitoring, signal analysis, genomic analysis, geocoding for epidemics, social media analysis, and so on. And to give you a taste of how these things are done, I will point out 3 examples, one of the short-term projects and 2 of the longer term. The first one is a wonderful collaboration and with Dr. Roger Coleman from Vascular and Interventional Radiology. The data lab staff on the project are Nick Yule, Michelle Tobias, and myself. So shout out to data lab people. I see about 6-7 of us here. Good showing. This is run as a data lab startup project where we dedicate 10 to 12 weeks of resources, and we work closely with Dr. Goldman to develop a strategy to solve his problem. And then we have dedicated data scientists who are working day to day on this. So what is the problem? Dr. Goldman is developing the UC Davis angiographic database. And this is a database of images and videos that are collected over thousands of procedures at UC Davis Health. And in particular, he is interested in the vascular diseases and interventions. And shown here is angiographic images of vascular of the vascular part of the vasculature of the whole body. Sorry, I lost my title of this slide. I should have known more about this, but what's shown is that we have images from different parts of the body, and Dr. Goldman has built a collection of 50,000 images, and the goal is to try to annotate these images and label them automatically based on some label training data. And so we use convolutional neural networks and other approaches to actually label these. In particular, for single angiographic image inference, we have used a transfer learning approach based on the Inception ResNet. And we got very good accuracy in training and validation. And shown to the right is a confusion matrix for predicting 5 different categories of vasculature. And oh yes, it was renal vasculature. That's what I was supposed to say on the previous slide. What we see here in the confusion matrix is that all that our methods work very well to classify these images. There's still some confusion going on, especially between the common hepatic artery and the celiac trunk artery. And the reason for that is because they're next to each other and they look alike. And the images that we use actually include both. So no wonder the network is getting confused with this. But as we introduce further more images from any given procedure and even movies of the procedures, we suspect some of this confusion will be resolved. So that's one of the collaborations, of the short-term collaborations. We're already at the tail end of it, and we are working together with Dr. Goldman to identify potential longer-term collaborations and funding. On the longer-term project side, what we have been engaged in is providing health data science know-how for hospital operations. Again, with the lead there, the IT Health, Dr. Jason Adams. We also have been doing case studies of synthetic patient data generation using open source software and public data sets. This is with Charlie Forneka, who is also here in the audience. And we have been in the past standing up secure and privacy preserving computational environments, which Dr. Anderson, a partner in crime here in our cluster, has been working on for a while. And we have been also doing something more social media oriented, scanning social media traffic for early identification of animal disease epidemic threats with Dr. Martinez Lopez. And I'm going to tell you about 2 of these things. One, which I'm very happy about and proud of, is the collaboration with Dr. Jason Adams and IT Health, and supported by Dr. Atreya. And this is about providing health data science know-how to help UCDH operations. Wes Brooks and Nick Yule from Data Lab are involved in this with funding from UCDH and Data Lab. So just to caricature, to present a simple problem, one of the problems we've been working on is to predict hospital admissions for COVID cases. And shown here is the response, which is the admissions, and it's a snapshot over a year from July 2020 to July 2021. We did daily new COVID-19 admissions on the y-axis. And given on the right are about 65 independent variables that the goal is to fit into a model and to then be able to predict the admissions. And this is important for efficient hospital operations, but also for anticipating need. And long story short, we did end up zeroing in on a particular model for the forecasting. And we select a number of features from all of those 65. But the more important thing here is to understand that when forecasting with such data, we recognize that there is dynamic and steady portions during the COVID pandemic, and we use that fact to actually build better models. So as compared to models that just say we're going to just use yesterday's data to predict what's going to happen tomorrow, our models do much better, as shown in the picture. And especially during the dynamic portions, during the steady portions, they're pretty much doing the same. But let me just point out the difficulties in doing something like this in an operations environment in the hospital, where the goal is to actually be able to implement this and provide it to doctors and nurses who are there on the ground dealing with these cases. So the problem is that as the pandemic progresses, things change. The assumptions we put in the model change. So we also developed a way to detect bias. How far are we away from the original assumptions of the model, and when do we need to retrain a model? And shown here, I'm not going to go into too much detail, but shown here is an example where adding data from the steady portions of the pandemic actually doesn't help much in prediction. What helps is adding data from the portions of the pandemic where there is growth or drop in the number of cases. So we developed a model to actually, given a bias percentage that we assume, how many admissions would be needed to detect it with a certain amount of power, particularly 80% power, so that we know when our algorithm is deviating from the assumptions based on the data that's coming in. And so finally, I wanted to point out the third example here, which outgrew from a startup project, and that is scanning social media traffic for early signs of animal epidemics. Data lab staff Tyler Shoemaker, the PI is Beatriz Martinez Lopez at VetMed, and this grew into a multi-year NSF, and Xin Liu is also involved in this. The point here is that by tracking Twitter and other social posts, we can potentially identify hotspots that can lead us into epidemic outbreak mitigation. And we're showing here just a word cloud of looking for animal diseases, all the tweets and the words present in there. And our goal is to develop linguistic models to actually analyze such data and take us to a tweet that's relevant and geographically tagged. So just skip through this just to say that we are developing these methods based on state-of-the-art linguistic neural network models and transformer models, and some preliminary results showing that we do in fact have a domain space that we can nicely cluster and identify in that domain space different clusters of activities coming from news aggregators, individuals, sick pets, and etc. So just to summarize in the last couple of minutes, what we've learned as doing these research as a service collaborations, and how we are growing our extension into the health data science. What we're learning is that research as a service has to be professional. We have to have high level of staff skill, both social and technical, and we have to pay particular attention to continuous upskilling. And this is something that Data Lab works on all the time. And we are able to be agile. We're able to provide feet on the ground for any project ready to go in days to weeks, with particular attention to the all the details stemming out of privacy and safety of medical data. We also are building up a hierarchy of skills, paying particular attention to this verticality, having science managers that can be interdisciplinary data scientists that are task-oriented postdocs, GSRs, and undergraduates all working together in teams. And we are putting forward these science-first vertical teams where we have science manager and team lead working with data scientists and the PIs on the projects. And so what's important for us is, and we are working on this all the time, is to have rich interactions. In other words, to have multi-level engagement with the PI and the PI's team. So not just our data scientists working on the data, but constantly reevaluating the research needs and the research directions and how that helps the PI. And so we recognize the different needs of shorter versus longer term engagements. And so we have developed these concepts of SWAT teams and embeds where we have more of an institutional memory. And finally, one of the most important parts is growing the community and understanding who is who and what is what at UC Davis. Particularly, we are growing this triaging and service network with other cores and entities, IT Health, CTSC, HPC, so that we know where to send people, what's appropriate for them, and how to best help them. So I want to give a shout out to our data lab staff, Carl and Pamela, our executive and associate leaders are here, and a number of other people, Michelle, Tyler, Wes, Arthur, Nick, and Charlie are all here from what I saw. So if you have any more questions, please contact me, and I'm happy to answer any questions here. Thank you.
Thank you, Vladimir. So with that, we're done with presentations, and this is a great time for our colleagues on the call and the webinar to present your questions to our speakers. I know that we had some active exchanges in the chat box, but if you want to turn on your microphone and either make a comment, share information, or ask a question, time. I have a question for those collaborators on the School of Medicine who works with the researchers who gave presentations today. If you could say a few words about your experience in being engaged in this, like sometimes very basic research, and what are some challenges and how you've addressed those. Kevin is nodding, so I'm going to call on him.
I was just thinking about how I find myself here today and among such amazing people. I think the first task was realizing that such a group exists. And I was fortunate, I emailed the interdisciplinary office of research, and that ended up helping connect me with Dr. Filkov, who I was so lucky to meet because he understands the group. And from there, I got to meet Chandni and Shin. And so I think things like the emails that you're sending out for these types of meetings and just simple first point of contacts were really key just to get something off the ground. And I think one of the things I've loved about working with the group is they've helped me understand in a bidirectional way what kind of data are useful, meaning we need more cases rather than controls, or and just learning how they operate in a way that will help us be more efficient in the future.
And Lucia, can I make a comment? I don't know whether Ashish is online. So one big challenge is access to medical data. And I know Ashish was working on some efforts on making that possible. So if Ashish is around or anyone from the health system can update on that.
I think it's Ashish's team and Rachel Calcutt. They are working together on how to make medical data accessible. But I think as Chandni presented at the beginning, it's a rather complex issue, and there are a number of ethical and legal considerations that will need to be taken. I think John Tupin is here. Maybe he can also comment on this, because he's right in the crux of all of this.
Yes, ma'am. We have been working on this issue with the team over at UC Davis Health, and they've been fantastic. We've got a couple of different avenues by which we are creating, they call them data lakes and anonymized data transfers and a couple of other techniques. Compliance has been very involved and it's been helping. And I'm very optimistic that we'll be able to create something that checks all the HIPAA boxes and allows people to run algorithms within the data pools that are created. And it's going forward, and I think we're making a lot of progress.
Yes, so every initiative, every ideas that come forward will have to be formalized in IRB applications, and will end up having to be approved by John Tupin's operations. So yeah, that's the way forward, Prasant. Did this answer your question?
Yeah, thank you.
Any other comments? I know we're like a little bit over our scheduled time.
I just saw some on the chat, like Rhino Health from someone, but also we have programs like Milo, developed by Nemtran and others. Are there any efforts to integrate all these parallel machine learning and AI programs, or it's not necessary?
I think there's a, hi, this is Richard.
Richard, yes.
Hi. I think there's a difference between Milo, which is a way to sort of scan many different machine learning tools in parallel and pick the best one, and the federated learning, which has in what Rhino Health does, has nothing to do with AI. They provide the infrastructure that allows the learning to occur locally and without transfer of precious data from one institution to another, and then you aggregate the hyperparameter scores or something. So they're completely different, but probably compatible.
Thanks. Yeah.
Sure.
So we are a few minutes over, and I know people probably need to head to their next meeting. I want to just thank everyone, especially our speakers, for the wonderful presentations today. We had a great attendance today for being the last session in the middle of December. This is a topic where there's a lot of interest, and so I'm looking forward to hearing from you. Maybe we can do another one of these in 6 months into the year and see where we are there. It seems like access to data is a question across the board. So maybe we can focus on that. And then just to echo Kevin's comment, if you're a researcher at the School of Medicine, or you're a researcher at the campus in Davis, and you're trying to get started here and you don't know who to contact, our group at Strategic Initiatives is happy to chat with you and help you figure out where to take your request. You can also contact directly CDAR, or you can contact directly Data Lab. But our team here at Strategic Initiatives is happy to be a switchboard for you and help you find resources on campus. We are working on the sessions for next year. We plan to have our first session on January 14th. So you'll be getting some emails from me, but if you are interested in having your team co-host a session with us, or you have a suggestion for a topic or a good lead or on an external speaker, please reach out to us and we'll be very happy to work with you. Have a great holiday break, and we'll see everyone in January.
Thank you, Ana Lucia.
Happy holidays.
Thank you, Ana Lucia.
Thank you.